So, continuing with our series of lectures on vectors, the last class we have found we have the addition of vectors geometrically, how to add vectors geometrically. So, we have found that to add vectors geometrically, we arrange the vectors in order such that the tail of the succeeding vector lies on the head of the preceding vector. Suppose we have two vectors A and we have to add vector B. That vector, the tail of that vector must be on the head of the A. So this will be, and the resultant is given by this straight line joining from the tail of the A to the head of the B. So this is where we can add vectors geometrically. So we will now solve some exercises. First example, exercise for you is, suppose we have two vectors, displacement vector say A is 10 meter north and B is 10 meter east. Now you have to add, to add vectors, what we have to do is first of all, we have to take a reference frame. So suppose we have taken a reference frame, this as our reference frame, this is our north-south and this is our east-west direction. This is east, west, north, south. Now, this 10 meter is to be converted to suitable scale. So let 2 meter is equal to 1 centimeter. So it means 5 centimeter line along this direction will represent vector A. Now on the blackboard the 5 centimeter line will be very small, so I am taking as an inch. You can take it as on your copy as a centimeter converter scale, but I am taking as inch. So 5 inch is here. So it is. So this length represents the vector. So the A has been drawn. Now the vector B. Now B has to be added to A. So it starts from here, from the head of A. And in the direction along east. So the direction of east is long. So it's again 5 inch line along this side, east side. So 5 inch line. This represents vector B. So the A plus B is this length. The resultant. Now, see, this is about 7 inches, 7.1 inches or 7.1 inches. So the length of the resultant vector is 7.1 inch into, converting into 2, this comes out to be 14.2 meter. And the direction is given, can be calculated by protractor, and this direction is about 45 or 46 degree. It's about 46 degree north of east. This is 60 north of east. So in this way we have added vectors geometrically. Very good. Now let us take another example, example 2. 10 meter east and B is 10 meter northeast, okay, northeast. So this means again converting 10 meter into 1 centimeter. So so 5-inch line A is on this side, so 5 inches line on this side is this vector A, and vector B is northeast from the head of A. So the northeast means making 45 degrees with east and 45 degrees with north. So dividing the northeast line. So it is 45 degrees. So 5 inch along this side. This makes 45 degree. So if this represents vector A, this represents vector B. The resultant is given by the straight line, an arrow joining from the tail of A to the head of B. So this is your resultant. So the length of the resultant is 7, 8, approximately 9.2 inches. So it is R is 9.2 into 2, 9.2 inches, and 1 inch is equal to 2 inches equal to 1 meter. So it is 18.4 meter. And to measure this angle, it's about 24, maybe 24 degree, approximately 24 degree north of. So in this way we can add, let us see, I have given you 2 examples and one more example. I will do one more example and then we'll move ahead. So the third example is A is 10 meter east, B is 10 meter 120 degree north of east. And C is 120 meter 120 degree south of east. So it's again converting the scale. Suitable scale is here. 2 meter is 1 centimeter. So it was 5 centimeter line along east. This represents vector A, and B is 120 degree north of east, means 120 degree make 120 degree along north from east direction. So it is this represents a vector 120 degree. Now vector C. Vector C is south of east. So this is from here, this is east. You have to make 120 degrees south from east. So it will be along. So this is the east line, and you have to take 120 degrees from this towards the south direction. So the south is here. So it's again 5 inches line and 5 inches line. Yes. This is your C. This is your B. So here the resultant is 0 because it closes the path, and we have found that when vectors are arranged in order and they form a closed path, the resultant is 0. So all these are 3 examples to just make you aware of how to add vectors geometrically. Now we'll move ahead to the next. So we have already found that if you arrange the vectors head to tail, the resultant is given by this straight line joining the from tail to initial to head of the final. So these are called the components, and this is called the resultant. So here A, B, C are the components of R, where R is the resultant of the vectors A, B and C. Okay. Now we are going to study some special kind of components, and those are called rectangular components. So the next is rectangular component. Let us have two vectors A and B, which we have, which are like this. Suppose there is a vector this is the vector A, and there is another vector B which is along this direction. And B makes an angle 90 degree with A. Obviously the resultant of A and B will be this straight line or this arrow from the tip of A to the head of B, and this is the resultant. Now in this case, if the two vectors, the components of a vector R, and the two components are at right angles to each other, they are known as, special name for them is rectangular components, not simple components. Here, if two components of vectors form, if two components of a vector are at right angles to each other, they are called rectangular components. Here A and B are the rectangular components of the vector R. Here A and B are the rectangular components of R. Okay. Now, again, suppose here again A and B are the rectangular components of the vector R. Now, suppose this makes an angle of, say, theta. So we can write A by R as cosine theta. So base by hypotenuse. So A is equal to R cos theta. Similarly, we can write B by R as sin theta, or B as R sin. So this is the relation between the rectangular components and their resultants. These rectangular components can be obtained from the resultant. This is the rectangular components. A component has a value equal to R times cosine theta, and B has a value equal to R sin times. We can take its values also. Cannot This one is simply length. So it's r cos theta and r sin theta. Its length is equal to r cos theta and its length is equal to r sin theta. So now it means you can resolve any vector into its two rectangular components. All we have to do is, suppose we have a vector. Any vector says P is a vector. Now we can have a large number of pair of rectangular components of P. Suppose all we have to do is to take one vector from the tail of B, one straight line from the tail of B, and another straight line perpendicular on this. So we have that rectangular components of P. We have resolved P into, suppose this is A1 and this is B1. So A1 and B1 are the rectangular components of P. Now you can take another rectangular components also. Suppose there is another vector here. So it is, and draw perpendicular on this. A2, B2. So A2, B2 is again the rectangular components of vector P. We can have another set of components also. Suppose this is another set of pair of rectangular components is A3 and so you can resolve any vector into a pair, into a large number of pair of rectangular components. So P can be written as A1 plus B1, or it can be written as A2 plus B2, or it can be written as A3 plus B3. All of them are equally correct. You can take any pair, but which one is to be taken will be depends upon the nature of the problem. Whether you have to take, it's better to take A1 plus B1 pair, or A2 plus B2 pair, or A3 plus B3 pair as rectangular components. That depends upon the nature of the problem, and we will do that. That which one is to be preferred over all these pairs. But the difference between that, the angles are different, so the values will be different. So suppose this makes an angle of alpha, and this makes an angle of theta, and this makes an angle of beta. So A2 will be equal to P cos theta, and B2 will be P sin theta. Now A1 is equal to, this is A1, this is angle, this is alpha. this is alpha. So it's A2 is P cos alpha and B2 is P sin alpha, and A1 and B1. So A1 is making angle theta. So it is A1 is P cos theta and B1 is P sin theta. And similar A3 is this and B3 is this, makes angle beta. So it is P cos beta, B3 is P sin. So now we know that as the angle increases, the cosine component decreases and sine component increases, because the value of sine and cosine varies like this. Zero, 30, 45, 60, 90. So as the angle increases, you find that the sine value of sine is sine 0 is 0. It's 1 by 2. It's 1 by root 2. It's root 3 by 2, and this is 1. The value of cosine is 1 root 3 by 2, 1 by root 2, 1 by 2. So as the angle increases, the value of sine increases and cosine decreases. So as larger the angle, the cosine component decreases and the sine component increases. So it's A2 is lesser than A1 because the angle is larger, and similarly, and if you if it becomes alpha, it becomes 0 or 90 degree. So this component becomes 0. Okay. So this is called the resolution of a vector into its pair of rectangular components. Okay. Now we will do some problem and we will find that which pair of rectangular components is to be taken in that case. But before that, I will do composition of vectors. No, you can do problems first. Do the problem. Then suppose we have block on the table. Block of mass, say M, and a force acts on this block. Force F. That's one. Now you can resolve this force into two rectangular components. So if you resolve this into a pair of rectangular components, suppose I have resolved it, drawn a straight line from the tail of this vector and a perpendicular on this. So this is one pair, this is another. But this, it means this block is acted upon by two forces, one is F1 and one is F2. And one of the, sorry, I have this one point to say that these two rectangular components are independent of each other and they act independently if F1 acts along this and F2. But this does not explain in our motion of the block. But if you take the components along this, suppose we consider another component, set of components. One of the components is say along the table, along the base of the table. And another component This is F1. Clearly, these two components are more understandable. That means F1 is responsible. The component which is along the parallel to the table is responsible for the motion of the block along this direction, and the component which is perpendicular on the table acts reaction to the table. So F1 is responsible for the motion of the block along the table, and F2 acts to the weight. Naturally, your choice of the pair of components will be these two, not that one, F1 and F2, because this solve our problem and how the motion takes place. The motion is due to the force F1 and not F2. F2 is just adding to the weight. It's mg here. So the reaction on the table will be mg plus F2, and that will be the weight. So in order to move the, and suppose this is angle theta. So the F1 is F cos theta and F2 is F sin theta. As it increases the angle of the force, the component F2 will increase and F1 will decrease. It means if you force, the direction of the force increases. Suppose in the direction of along this, you take this, so the angle increases. As the angle increases, this component decreases, F1 component, which is responsible for the motion, and F2 component which adds to the weight. So this, if you make 90 degree, so only this component remains. If suppose theta is equal to 90, so this component becomes cos 90 is 0, so F1 will be 0. If theta is 90, F1 will be 0 and F2 will be equal to F. So all the force F is acting along this direction. Just so in order to move the block, what we will do, that will decrease the angle. So instead of applying force along this direction, you apply like this or this. If you decrease the angle, then F1 will be equal to F. Suppose theta is 0. So F1 will be equal to F and F2 is equal to 0. So as it decreases the angle, this becomes, and all the forces along this direction. So the motion. And we usually do that when we push up any heavier blocks and it's not moving, we just makes this angle like this. Instead of pushing like this, we take this line. So this all. Now, so if you want to add to the weight, as for example, if you have a lawn mower, a roller, now if apply force here, I suppose this is a lawn mower or a roller, suppose this is a roller. You apply force here, its component will be along this direction and this direction or this direction. So instead of, if you want to push the, increase this vertical component, what you do is increase this angle so that this may push the ground with more force. So of the block along this direction. And take the two components. Naturally you will find that these are two components. It's easier to take these two components. F1 and Mg is along this direction. So F1 is responsible for the motion of the block, sliding of the block, and F2, which acts vertically upward, decreases the reaction on the surface. So it's easier to pull than to push. In pushing you are adding to the weight, and pulling you are decreasing the force. So the weight here becomes F2 minus mg, and the F1 is responsible for the motion. So take one more example. Suppose the block is on an inclined plane. The weight acting on the block is along this direction, mg. Is the vector quantity, is the force acting towards the center. Now you can resolve these in order to explain this motion. What we'll do that is resolve this vector into two rectangular components. And the one component, obviously, this one component will be your first choice will be that the first component must be along this direction, along the inclined plane, and another component will be perpendicular. So this component, suppose this component is this is theta, and suppose this is actually this is also theta. So this component will be instead of mg I am writing with w. So this will be w sine theta, and this component will be w cos theta. This is component will be. So the w sine theta is responsible for the motion of the block along the table, and w cos theta just pushes the block or add to the reaction of the block. Okay. Now, composition of position we have just found that we have vector, any vector, say R. If this can resolve into two rectangular components, suppose the rectangular components is A and B, making an angle of say theta. So obviously A is R cos theta and B is R sin theta. Now suppose we know the rectangular components and we have to find its resultant. Suppose we know A and B. We have given B and this is the resultant, and we do not know the resultant. So what we do, in order to find its magnitude, what we do, just to find the magnitude of R. Of the resultant vector, R is the resultant of A and B, and we suppose this resultant makes an angle of theta with A, then we know that A can be written as R cos theta and B can be written as R sin theta, in order to find its magnitude and its direction, theta. So what we have to do is just square and add. So if you square and add, you will get a square plus b square is equal to r square comma cos square theta plus sin square theta, which is r square, because this cos square theta plus sin square theta is 1. So the resultant is given by, the magnitude of the resultant is given by this, by a square plus b square under root, and the direction is given by this theta. So the direction is direction of r can be as well divide these two. If you divide, you will get b by a sin theta by cos theta, r cancels out. So it is tan theta, which give you phi. So in this way we have found the magnitude and the direction of the resultant. This is called the composition of vectors. We have given two vectors which are at right angles to each other. You can find the magnitude of the resultant there and the direction of that. So all these about the resolution of vectors and composition of vectors. So now in the next class we will add further and how to add vectors analytically. Till now we have found the addition of vectors geometrically. Now in the next class we will work out how to add vectors analytically.